Right. So we're going to start our look at the source filter business with a look at resonances in tubes. So the fundamental idea that most people are familiar with in one way or another is that there are objects which like to vibrate at a particular frequency. Musical instruments are a great example. Shorter strings vibrate at a higher frequency than longer strings, and more relevant to speech, for like wind and brass instruments, you get a lower note when you're blowing through a longer tube than when you're blowing through a shorter one. You know, there's a lot more to it than that, but this is linguistics, not music, and this will do for me. So there's this fascinating phenomenon in air-filled tubes that gives us this property, where when sounds bounce around in a space, uh, they can reinforce themselves, or they can do the opposite. They can kind of cancel themselves out. When they reinforce themselves, we get what's known as a standing wave, and this is the note that you hear in those nicely resonating structures. A standing wave is where, as a wave bounces back and forth, it produces what look like pressure fluctuations that are standing still rather than traveling through space. So rather than seeing, you know, pressure as this sort of traveling wave, traveling high pressure and low pressure areas sort of following each other, you get pressure going up and down in some places and staying almost uh, unchanged in other places. Um, and what's more, we know enough about the way the air particles move and how they like to build those standing waves that we can predict what frequencies are likely to reinforce themselves based on the length of the tube. Uh, And it connects to wavelength. Remember, we have a formula connecting wavelength and frequency, I'm sorry, wavelength and the speed of sound to frequency. So you see, when a wave is oscillating back and forth in place, there's areas where the pressure is changing a lot, and there's areas where it's not changing much or at all. The areas of minimal change are called nodes, and the areas of maximal change are called antinodes. You think of a node as, you know, sort of something as uh, collected together. An antinode is the opposite. So different types of tubes support different types of standing waves, but uh, we're going to look at a tube that's closed at one end and open at the other. Why? Because that's a reasonable approximation of the vocal tract, and we'll get to that more as we go along. Um, in a tube, when we get a standing wave, there's a few things that we can kind of reason out from basic principles. First, any movement of air at the air particles up by the closed end of the tube will tend to change the pressure a lot because the other air particles can't move out of the way as easily. If we get a little bit of movement together, they can't get out of the way, so the pressure is just going to go up uh, quickly. So we find an antinode there where pressure varies maximally. At the open end of the tube, on the other hand, that's where particles have the whole world to slip away into if they get pushed on, and we have a whole world of particles to come back in if it goes the other way. So the pressure hardly varies at all because there's this very easy movement. That's a pressure node. So we have an antinode at the closed end and a node at the open end. And I'm just going to show you, uh, here is an example of an illustration where you see at the left the open end of the tube, at the right closed end. And this sort of paired portion fragment of a sine wave is a popular way to display uh, these standing waves, because at the open end the pressure is not going to be varying at all. But if we measure pressure here, it's going to vary a bit. And the closer we get to the antinode, the more the pressure is going to vary. So it goes all the way up to the top and all the way down to the bottom. But you notice either arm of that is kind of like a fragment of a sine wave. And we're going to get to that. I'll get back to that in a second here. Um, but there's more. That's one wave that could resonate in this space. That could, one frequency or wavelength, I guess, that could form a standing wave there. But there are others, right? Because you could have a wave that has a shorter wavelength that's just short enough that you can fit an extra half of a cycle in. So you have an extra antinode uh, and an extra node between the node at the open end and the node at the antinode at the closed end. Okay, so the second resonance has two nodes and two antinodes. The first resonance, if you remember, has one of each. And in fact, that's a nice reliable relationship. The number of nodes that fit in gives you the number of the resonance. And yeah, so what we can do from there, um, we know that frequency is equal to the speed of sound divided by the wavelength. And if we do a little bit of math, we don't have to worry too much about how to get here, but here's a formula that gives us that for all of the resonances in a uniform cylinder like that. So the frequency of resonance K equals 2 times K minus 1, all multiplied by the speed of sound over 4 times the length of the tube. So as the resonance goes up, the frequency goes up, and the wavelength will become shorter, of course. Okay, so that's resonance in a cylindrical tube. And just to finish this video off, let's talk a little bit about when the tube isn't perfectly cylindrical, because we know in the vocal tract it isn't. In fact, one of the main ways that we make different sounds is by changing the shape of the vocal tract, by moving the articulators around, right? So the textbook gives us some detail about what happens to our nice mathematical picture we just saw when we have a narrowing or a widening somewhere in the tube. And each resonance is affected differently depending on whether that change is close to a node or close to an antinode or somewhere in between. My favorite way to remember is this. If the constriction happens at a pressure antinode, such as the closed end of the tube, where pressure is varying a lot, you have a constriction, suddenly there's even less space for the particles to fit into and to get out of the way, so pressure is going to rise that much more quickly. And as the particles move away, pressure is going to drop that much more quickly because there's fewer particles to take up to fill in that space. So pressure is going to be varying more rapidly, which gives you a higher frequency oscillation. So if you constrict at a pressure antinode, you raise the frequency of that resonance. On the other hand, if you have the open end or somewhere else that's a pressure node, right, where the pressure isn't varying a lot because the particles can move back and forth very freely, well, if you constrict there, suddenly you're getting in the way of that free movement. So the particles aren't going to be able to move quite as quickly. So a constriction at a pressure node slows down the particles and it reduces the frequency of the wave. And then when you have widenings instead of constrictions, you just have the opposite effect. All right. So that is, in a nutshell, the idea of resonance in a tube. Resonance in a uniform tube, and then as you depart from uniform. So have some fun with that. And you can imagine where we're going to be going with that, and we'll get deeper into that in the coming videos.